The mole concept, part 1. We will realize that depicting a chemical change on the basis of the number of particles, atoms, molecules or ions is of greater significance than doing so on the basis of their masses. H2 gas 2 atoms plus Cl2 gas 2 atoms gives twice HCl gas 2 molecules. Ag plus aqueous 1 ion plus Cl minus aqueous 1 ions gives Ag plus Cl minus solid or AgCl, one formula unit. Atomic and molecular masses are measured with respect to C12, so let us try to see if the number of atoms in a gram atom of an element is related in some way to that in 12 grams of 12C. Suppose the relative atomic mass of an element A is X. Hence 1 gram atom of A weigh X grams. Let the number of atoms in 12 grams of carbon 12 be N, and that in 1 gram atom of A be N dash. Therefore, N into mass of 1 atom of carbon 12 is equal to 12 grams, and N into mass of 1 atom of A is equal to X grams. So, N dash into mass of 1 atom of A divided by N into mass of 1 atom of C12 is equal to X gram by 12 grams. N dash by 12 into N into mass of 1 atom of A divided by 1 by 12 into mass of 1 atom of C12 is equal to X by 12. N dash by 12 into N into relative atomic mass of A is equal to X by 12. N dash by 12 into N into X is equal to X by 12. So N dash is equal to N. Thus, 1 gram atom of an element has the same number of atoms as that in 12 grams of carbon 12. We can easily prove this to be true for the number of molecules in 1 gram molecule and that of ions in the 1 gram ion of any kind. An assemblage of this number of particles is known as a mole. Mole when used as a unit, which may be defined as follows. The mole concept, part 2. A mole is the amount of a substance that contains the same number of particles, atoms, molecules or ions as the number of atoms in exactly 12 grams of carbon 12. We will learn in higher classes that concept of mole has been extended to electrons and other elementary particles too. This number of particles, the presently accepted value of which is 6.022 into 10 to the power 23, previously called the Avogadro number, is of great fundamental significance. Nowadays, the term Avogadro constant Na is preferred, which is simply the Avogadro number suffixed by the unit of mole raised to power -1. The Avogadro constant is equal to 6.022 into 10 to the power 23 mole raised to power -1. Thus, an assemblage of 6.022 into 10 to the power 23 particles is a mole. Gram atomic and gram molecular masses and the mole concept. Let us look at gram atomic and gram molecular masses on the base of the mole concept. We can easily understand that the gram atomic mass or the gram atom of an element is a mole of it, which is the mass in grams of the same number of atoms as contained in exactly 12 grams of C12. We can easily arrive at the following important relationships. First, 1 mole of atoms of an element is equal to number of atoms in 1 gram atom of the element equal to 6.022 into 10 to the power 23 atoms. Second, the absolute mass of 1 atom of an element is equal to gram atomic mass divided by 6.022 into 10 to the power 23 equal to relative atomic mass into 1.66 into 10 to the power -24 grams. Third, in a given mass of an element, A, the number of moles of atoms is equal to the number of gram atoms is equal to mass of the elements in grams divided by gram atomic mass. B, total number of atoms is equal to the number of moles into N by A is equal to mass of the element in grams divided by gram atomic mass into 6.022 into 10 to the power 23. Let us take some examples. If you need 3.011 into 10 to the power 23 atoms of sodium of Na for a chemical reaction, what is the mass of the metal required? Relative atomic mass of Na is equal to 23. Let's solve this. The gram atomic mass of Na is equal to 23 grams. For 6.022 into 10 to the power 23 atoms of Na, the mass of the metal required is equal to 23 grams. Therefore, for 3.011 into 10 to the power 23 atoms of Na, the mass of the metal required is equal to 3.011 into 10 to the power 23 divided by 6.022 into 10 to the power 23 into 23 grams is equal to 11.5 grams. The mole concept. Part 3. Let's take the next example. How many moles of chlorine atoms are there in 106.5 grams of chlorine? Relative atomic mass of chlorine is equal to 35.5. Let's solve this. In a given mass of the element, the number of moles of chlorine atoms is equal to number of gram atoms is equal to mass of the element in grams divided by gram atomic mass is equal to 106.5 grams divided by 35.5 grams is equal to 3. The gram molecular mass of a substance is a mole of it, which is the mass in grams of the same number of molecules or formula unit of the substance as the number of atoms contained in exactly 12 grams of 12C. The following important relationships can be easily derived. 1 mole of molecule of a substance is equal to number of molecules in 1 mole of the substance equal to 6.022 into 10 to the power 23 molecules. Second, the absolute mass of 1 molecule of a substance is equal to the gram molecular mass of the substance divided by 6.022 into 10 to the power 23 in grams. Third, in a given mass of a substance, A, the number of moles is equal to mass of the substance in grams divided by gram molecular mass. B, the total number of molecules is equal to the number of moles into 6.022 into 10 to the power 23 is equal to mass of the substance in grams divided by gram molecular mass into 6.022 into 10 to the power 23. C, the number of atoms of a given element constituting the substance is equal to the number of moles of the substance into the number of atoms of the element in 1 molecule of the substance into 6.022 into 10 to the power 23. D, the total number of atoms is equal to the number of gram molecules of the substance into the total number of atoms in a molecule of the substance into 6.022 into 10 to the power 23. Let us take some examples. How many moles of HCl molecules are there in 109.5 grams of HCl? Calculate the number of molecules in the sample. Atomic mass of hydrogen is equal to 1 and that of chlorine is equal to 35.5. Solution. The relative molecular mass of HCl is equal to 1 plus 35.5 equal to 36.5. The number of moles of HCl molecules in 109.5 grams is equal to mass of HCl in grams divided by gram molecular mass is equal to 109.5 grams divided by 36.5 grams is equal to 3. The number of HCl molecules in 109.5 grams is equal to number of moles into 6.022 into 10 to the power 23 is equal to 3 into 6.022 into 10 to the power 23 is equal to 18.066 into 10 to the power 23. The mole concept, part 4. Let's take the next example. The mass of an atom of an element is 3.986 into 10 to the power minus 26 kg. Find the relative atomic mass of the element and identify it. Let's solve this. The mass of one atom of the element is equal to 3.986 into 10 to the power minus 26 kg is equal to 3.986 into 10 to the power minus 23 grams. Therefore, mass of 1 mole or 6.022 into 10 to the power 23 atoms of the element is equal to 3.986 into 10 to the power minus 23 into 6.022 into 10 to the power 23 grams is equal to 24 grams. So the relative atomic mass of the element is equal to 24. The element of relative atomic mass 24 is magnesium. A mole of ions. Ions are formed by the loss or gain of electrons from or by an atom. The mass of electrons being negligible, ions are considered to have the same mass as the parent atoms. The mole of ions is defined as the assemblage of the same number of ions as the number of atoms in exactly 12 grams of C12. In other words, a mole of ions is an assemblage of 6.022 into 10 to the power 23 ions. Its mass, called the gram ions, is the same as the gram atom of the element from which it is derived. For example, mole of Na plus ions is a collection of 6.022 into 10 to the power 23 Na plus ions, which collectively weigh 23 grams. Similarly, mole of Cl minus ions is an assemblage of 6.022 into 10 to the power 23 Cl minus ions, which collectively weigh 35.5 grams. 1 mole of NaCl will furnish 1 mole each of Na plus and Cl minus ions. NaCl gives Na plus Cl minus. 1 formula unit of NaCl gives 1 ion of Na plus and 1 ion of Cl minus. 1 gram molecule of NaCl will give 1 gram ion of Na plus and 1 gram ion of Cl minus. So 1 mole of NaCl will give 1 mole of Na plus and 1 mole of Cl minus. Let us take an example. How many moles of Ca2 plus and Cl minus ions will be furnished by 444 grams of CaCl2? Atomic mass of calcium is 40 and that of chlorine is 35.5. Let's solve this. The relative formula for CaCl2 is 40 plus 2 into 35.5 is equal to 111. The number of moles of CaCl2 in 444 grams is equal to mass of CaCl2 grams divided by gram formula mass is equal to 444 grams by 111 grams is equal to 4. So, 1 mole of CaCl2 gives 1 mole of Ca2 plus and 2 moles of Cl minus. So, 4 moles of CaCl2 will give 4 moles of Ca2 plus and 8 moles of Cl minus. So, 444 grams of CaCl2 will furnish 4 moles of Ca2 plus ions and 8 mole of Cl minus ions. Empirical and molecular formulae, Part 1. Empirical and molecular formulae from percentage composition. Empirical formula. The empirical formula of a compound shows the atomic ratio of the elements present in a molecule of the compound. For example, the empirical formula of hydrogen peroxide H2O2 is HO because the simplest atomic ratio of hydrogen and oxygen in a molecule is 1:1. The empirical formula of a compound can be calculated from its percentage composition in the following steps. First, tabulate the percentage composition of the compound. This gives the mass of each element in grams present in 100 gram of the compound. Second, divide the percentage of each element by its relative atomic mass to obtain the number of moles of atoms of the element present in 100 grams of the compound. Third, divide the numbers of moles by a suitable common factor to obtain them in the simplest whole number ratio. Fourth, deduce the empirical formula of the compound from the whole number ratio of the atoms. Empirical and molecular formulae, Part 2. Let's take an example. Determine the empirical formula of a compound if it contains 5.9% hydrogen and 94.1% oxygen. Let's solve this. Let us make a table with columns, element, percentage, relative atomic mass, moles of atom, and atomic ratio. Elements present in our given compound are H and O, and percentage given in the question is 5.9 for hydrogen and 94.1 for oxygen. We know relative atomic mass of hydrogen is 1 and that of oxygen is 16. Dividing percentage by relative atomic mass, we will find the moles of atom. 5.9 divided by 1 is equal to 5.9, and for oxygen, 94.1 divided by 16 is equal to 5.9. Now we will divide the number of moles by 5.9 to obtain the simplest whole number ratio. So atomic ratio comes here as, for hydrogen, 5.9 divided by 5.9 is equal to 1. For oxygen, 5.9 divided by 5.9 is equal to 1. Therefore, the empirical formula is HO. Let's take the next example. An organic compound containing only C, H and O has 6.7% hydrogen and 40% carbon. Determine its empirical formula. Let's solve this. C and H account for 40 plus 6.7 equal to 46.7% of the compound. The rest, 100 minus 46.7 equal to 53.3% must be oxygen, as the compounds contain only C, H and O. Once again, let's make a table with columns, element, percentage, relative atomic mass, moles of atom, atomic ratio. So the elements we have are hydrogen, carbon and oxygen. Their respective percentages are 6.7 for hydrogen, 40 for carbon, 53.3 for oxygen. Relative atomic mass of hydrogen is 1, that for carbon is 12, and for oxygen is 16. For finding the mole of atoms, we will divide percentage by relative atomic mass. For hydrogen, 6.7 divided by 1 is equal to 6.7. For carbon, 40 divided by 12 is equal to 3.33. For oxygen, 53.3 divided by 16 is equal to 3.33. For finding the atomic ratio, we will divide the mole of atoms by a suitable number to get a simple whole number ratio. So we will divide mole of atoms here by 3.333. So for hydrogen, 6.7 by 3.33 is equal to 2. For carbon, 3.33 divided by 3.33 is equal to 1. For oxygen, 3.33 divided by 3.33 is equal to 1. So the empirical formula is CH2O. Let's take the next example. Ammonium chloride contains 31.8% NH3 and 66.3% chloride ion. Work out the empirical formula of compound H is equal to 1, N is equal to 14, O is equal to 16 and chlorine Cl is equal to 35.5. Let's solve this. Ammonium and chloride ion account for 31.8 plus 66.3 equal to 98.1% composition. The remaining percentage, that is 100 minus 98.1 is equal to 1.9, must be accounted for by the H plus ion attached to NH3 forming NH4 plus. So, the percentage of NH4 plus is equal to 31.8 plus 1.9 is equal to 33.7. Now let's make a table for finding out the empirical formula. In our table, once again, the columns will be ion, percentage, relative ionic mass, moles of ions, ionic ratio. In the first column, we write the ions NH4 plus Cl minus. Their percentages are for NH4 plus it is 33.7 and for Cl minus it is 66.3. Relative ionic mass for NH4 plus is 18 and that for Cl minus is 35.5. Next, we will find the moles of ions. Here we will divide the percentage by relative ionic mass. For NH4 plus 33.7 divided by 18 is equal to 1.87. For Cl minus 66.3 divided by 35.5 is equal to 1.87. Now we will divide the moles of ions. 1.87 divided by 1.87 is equal to 1. And for Cl minus 1.87 divided by 1.87 is equal to 1. Therefore, the empirical formula of ammonium chloride is NH4Cl. Empirical and molecular formulae, Part 3. Molecular formula. The molecular formula can be derived from the empirical formula when the molecular mass of the compound is known. As you know, the empirical formula gives the ratio of the atoms of the elements present in a molecule of a compound. The molecular formula gives the actual number of atoms of the different elements present in a molecule of the compound. Molecular formula is equal to empirical formula N, where N is an integer. Therefore, relative molecular mass is equal to N into empirical formula mass. So, if we know the empirical formula mass and the relative molecular mass, we can calculate N and thus determine the molecular formula of the compound. The relative molecular mass of a substance can be calculated from the relative density or the vapor density or determined by other methods. Let's take an example here. Deduce the molecular formula of a compound whose empirical formula is CH3 and relative molecular mass is 13. Let's solve this. Let the molecular formula be N times CH3. The empirical formula mass is equal to 12 for carbon plus 3 for hydrogen equal to 15. We know that N into empirical formula mass is equal to relative molecular mass. This implies N into 15 is equal to 30. This implies N is equal to 30 by 15 is equal to 2. Therefore, the molecular formula of the compound is CH3 whole twice, that is C2H6. Problems based on chemical equations. A chemical equation gives a lot of information about a reaction. The following steps will help you solve various problems based on chemical equations. First, write a chemical equation to represent the reaction and balance it. Second, write the number of moles of each reactant and product. These numbers are the same as the numbers of molecules or ions on both sides of the equation. Third, convert the number of moles of each reactant and product into mass or volume if gaseous, as convenient or required. Fourth, calculate the mass or volume of one or more of the reactants and products on the basis of the data given. Empirical and molecular formulae, Part 4. Let's take the next example. Acetylene and benzene have the same empirical formula CH, but vapor densities of 13 and 39 respectively. Reduce their molecular formulae. Let's solve this. Relative molecular mass is equal to twice into vapor density. If the molecular formula be N times CH, N into empirical formula mass is equal to relative molecular mass. This implies N is equal to relative molecular mass divided by empirical formula mass, and empirical formula mass is equal to 12 plus 1 equal to 13. Let's make a table here. Columns in the table are compound, vapor density, relative molecular mass, and molecular formula. Let us first take acetylene. Vapor density is 13. Relative molecular mass will be twice of vapor density, that is 2 into 13 is equal to 26. N is equal to 26 by 13 is equal to 2. Molecular formula will be CH whole twice, that is C2H2. Next we take benzene. Vapor density is 39. Relative molecular mass will be twice into vapor density, that is twice into 39 is equal to 78. N will be 78 by 13, that will be 6. Molecular formula will be CH 6 times, that is C6H6. So the molecular formula of acetylene is C2H2 and that of benzene is C6H6. Let's take an example. What is the mass of the quicklime and volume of the carbon dioxide measured at STP produced when 200 grams of pure limestone is strongly heated? Calcium is equal to 40, carbon is equal to 12, and oxygen is equal to 16. Let's solve this. The relative molecular or formula mass of calcium carbonate is equal to 40 for calcium, 12 for carbon, 3 into 16 for oxygen, and this is equal to 100, and that of calcium oxide is equal to 40 plus 16 is equal to 56. The number of moles of calcium carbonate in 200 grams of the pure sample is equal to 200 by 100 is equal to 2. The balanced chemical equation for the reaction is calcium carbonate solid on heating gives calcium oxide solid plus carbon dioxide gas. So 1 mole of calcium carbonate gives 1 mole of calcium oxide and 1 mole of carbon dioxide. Multiplying both sides of the equation by 2, we have 2 moles of calcium carbonate will give 2 moles of calcium oxide and 2 moles of carbon dioxide. So, for calcium oxide, 2 moles means 2 into 56 grams. 2 into 56 grams is equal to 112 grams. And for carbon dioxide, 2 moles will mean 2 into 22.4 liters at STP equal to 44.8 liters STP. Therefore, the mass of calcium oxide produced is equal to 112 grams and the volume of carbon dioxide produced is equal to 44.8 liters. This is measured at STP. Numerical and molecular formulae. Let's take the next example. What is the mass of barium sulfate precipitated when a solution prepared from 4.886 grams of BaCl2.2H2O treated with an excess of an S2SO4 solution? Barium is equal to 137.3, chlorine is equal to 35.5, sulfur is equal to 32 and oxygen is equal to 16. Let's solve this. The relative formula mass of barium sulfate is equal to 137.3 for barium plus 32 for sulfur plus 4 into 16 for oxygen. This comes as 233.3. Relative formula mass of barium chloride .2H2O is equal to 137.3 plus 2 into 35.5 plus 2 into 2 plus 16 is equal to 244.3. Therefore, the number of moles of barium chloride in 4.886 grams of barium chloride .2H2O is equal to 4.886 divided by 244.3 is equal to 0.02. The balanced chemical equation for the reaction is barium chloride aqueous plus S2SO4 aqueous gives barium sulfate solid plus twice HCl aqueous. That means 1 mole of barium chloride and 1 mole of sulfuric acid gives 1 mole of barium sulfate. So this will imply 0.02 moles of barium chloride and 0.02 moles of H2SO4 but present in excess will give 0.02 mole of barium sulfate, and 0.02 mole of barium sulfate will mean 0.02 into 233.3 grams is equal to 4.666 grams. So amount of barium sulfate precipitated is equal to 4.666 grams. Let's take the next example. Pure iron filings weighing 5.58 grams are placed in solution containing an excess of copper sulfate. Enough time is allowed for the reaction to be completed. What is the mass of the copper deposited? Cu is equal to 63.5, Fe is equal to 55.8, S is equal to 32 and oxygen is equal to 16. Let's solve this. The number of moles of iron in 5.58 grams of it is equal to 5.58 grams divided by 55.8 grams is equal to 0.1. The balanced chemical equation for the reaction is copper sulfate aqueous plus iron solid plus Fe solid gives FeSO4 aqueous plus copper solid. So 1 mole of copper sulfate and 1 mole of iron gives 1 mole of copper. This implies excess of copper sulfate, 0.1 mole of iron will give 0.1 mole of copper solid, which will be equal to 0.1 into 63.5 grams, which is equal to 6.35 grams. The amount of copper deposited is equal to 6.35 grams. This is our answer. Part 1. The volume occupied by 1 mole, that is 1 gram molecular mass of a gas, is called the molar volume of the gas at a given temperature and pressure. As the volume of a gas is dependent on temperature and pressure, they must be mentioned along with the molar volume. Standard molar volume. If the molar volume is taken at STP, it is called the standard molar volume or the molar volume at STP. The standard molar volume of a gas is defined as the volume occupied by 1 mole, that is 1 gram molecular mass of the gas at STP. Avogadro's law suggests that a collection of 6.022 into 10 to the power 23 molecules, that is 1 mole of different gases, will occupy the same volume at STP. Thus, if we calculate the standard molar volume of any gas, say nitrogen, it will be the standard molar volume for other gases too. The standard molar volume of nitrogen is equal to the gram molecular mass of nitrogen divided by density of nitrogen at STP. This is equal to 2 into 14.007 grams divided by 1.2505 grams per liter is equal to 22.4 liter. So the standard molar volume of a gas is equal to 22.4 liter. Thus, as the molecular mass of hydrogen is 2 grams of hydrogen occupies 22.4 liter at STP. Similarly, 2 into 16 is equal to 32 grams of oxygen will occupy 22.4 liters at STP. Some more examples as in the table. Example 1. What is the volume occupied by 17.75 gram of Cl2 at STP? Let's solve this. The relative molecular mass of Cl2 is equal to twice into 35.5 is equal to 71. The volume of 1 mole, that is 71 gram of Cl2 at STP, is equal to 22.4 liter. Therefore, the volume of 17.75 gram of Cl2 at STP is equal to 17.75 gram divided by 71 gram into 22.4 liter is equal to 5.6 liter. Let's take the next example. What will be the mass of 1.4 liter of carbon dioxide at STP? Let's solve this. The relative molecular mass of carbon dioxide is equal to 12 plus 2 into 16 is equal to 44. The mass of 22.4 liter of carbon dioxide at STP is equal to 44 grams. Therefore, the mass of 1.4 liter of carbon dioxide at STP is equal to 1.4 liter divided by 22.4 liter into 44 grams is equal to 11 by 4 grams is equal to 2.75 grams. Molar volume, part 2. Molecular mass from vapor density. The density of a gas relative to that of hydrogen at the same temperature and pressure is known as vapor density or the relative density of the gas. Thus, the vapor density of a gas is equal to density of the gas at given P and T divided by density of hydrogen at the same P and T, equal to mass of the given volume of the gas at given P and T divided by mass of the same volume of hydrogen at the same P and T. This is equal to mass of 22.4 liter of the gas at STP divided by mass of 22.4 liter of hydrogen at STP is equal to 1 gram molecular mass of the gas divided by 2 grams. Therefore, the relative molecular mass of a gas is equal to twice into vapor density. The vapor densities of gases can be determined experimentally. Many substances like methanol, ethanol and acetone can be completely volatilized. Thus, it is easy to determine the relative molecular masses of such substances. Here is the table of some common substances with their relative molecular mass. Example 3. The vapor density of carbon dioxide is 22. What will be the volume of 88 grams of carbon dioxide at STP? Let's solve this. The vapor density of carbon dioxide is equal to 22. Therefore, the relative molecular mass of carbon dioxide is equal to 2 into 22 is equal to 44. The number of moles of carbon dioxide in 88 grams of it is equal to 88 grams divided by 44 grams is equal to 2. The volume of 1 mole of carbon dioxide at STP is equal to 22.4 liter. Therefore, the volume of 2 mole of carbon dioxide at STP is equal to 44.8 liter. So the volume of 88 gram of carbon dioxide at STP is equal to 44.8 liter. Let us now understand about atomicity. The atomicity of a gaseous element can be easily calculated if we know the vapor density and atomic mass of the element. Atomicity is equal to relative molecular mass divided by relative atomic mass is equal to twice into vapor density divided by relative atomic mass. For example, the vapor density of nitrogen is 14, and so the relative molecular mass is equal to twice into 14 is equal to 28. As the relative atomic mass of nitrogen is 14, the atomicity is equal to 28 by 14 is equal to 2, hence the molecular formula N2. Stoichiometry. We know that an atom combines in whole number ratios to form compounds, and also the reactants and products appear in chemical equations in simple ratios. The relative proportions of elements in a compound or those of the reactants and products in a chemical reaction is known as stoichiometry. Percentage composition. The percentage composition of a compound in terms of the different elements constituting it can be easily calculated if we know the molecular or the empirical formula of the compound and the atomic masses of its constituents. Let us take some examples. Calculate the percentages of hydrogen and oxygen in water. H is equal to 1 and O is equal to 16. Let's solve this. The relative molecular mass of water is equal to 2 into 1 plus 16 is equal to 18. 18 grams of water contains 2 grams of hydrogen and 16 grams of oxygen. Therefore, 100 grams of water contains twice into 100 by 18 grams equal to 11.11 grams of hydrogen and 16 into 100 by 18 grams equal to 88.89 grams of oxygen. So, water contains 11.11% of hydrogen and 88.89% of oxygen. Important point to note here is sum of the percentages of all elements of a compound must be 100. In this case, 11.11 plus 88.89 is equal to 100. Let us take another example. Calculate the percentage composition of ethanol C2H5OH in terms of CH and O. Let's solve this. The relative molecular masses of C2H5OH or C2H6O is equal to twice into 12 plus 6 into 1 plus 16 is equal to 46. So in 46 grams of C2H5OH, twice into 12 equal to 24 grams of carbon is there, 6 into 1 equal to 6 grams of hydrogen, and 16 grams of oxygen is there. So in 100 grams, amount of carbon will be 24 by 46 into 100 grams is equal to 52.17 gram. Quantity of hydrogen will be 6 by 46 into 100 gram is equal to 13.04 grams. And quantity of oxygen will be 16 by 46 into 100 grams is equal to 34.78 grams. So C2H5OH contains 52.17% carbon, 13.04% hydrogen and 34.78% oxygen. Let us verify this. The sum of the percentages is equal to 52.17 plus 13.04 plus 34.78 equal to 99.99 is equal to approximately 100.